Hello everyone, welcome to Lecture 16 in our Stat 200 Introduction to Statistics course series. I hope this lecture finds you well. This actually should be a fairly short lecture, so I hope you pay attention. Okay, before we get started, I'll go ahead and start off with the joke of the day. I'll let you take a second. I would recommend pausing the lecture at this point and go ahead and read this whole thing because it's kind of long and it's pretty funny. Okay, I'm going to go ahead and advance, so if you haven't paused it and you're not finished, you might want to do so. Okay, so up to this point, or for the last couple of lectures, we've talked about continuous probability distributions. We're going to continue that today. We're going to talk about actually using a continuous distribution, the normal, to approximate a discrete distribution, the binomial. All right. So as I mentioned, in this section we're going to talk about some methods for using a normal distribution as an approximation for the binomial probability distribution. We have a couple of requirements that must be satisfied before we can do this. The first is that NP has to be greater than or equal to 5. And in this case, N is the number of samples that we're looking at. P is the probability of success in each trial or sample. N times Q also has to be greater than or equal to 5, where N is the number of trials. Q is the probability of failure for each trial. So if both those are satisfied, then the probabilities from a binomial probability distribution can be approximated well using a normal distribution with the mean given by mu equals N times P and the standard deviation given by sigma equals the square root of N times P times Q. I'm not going to present or discuss or show you the derivation where those two equations came from. If you're really interested and would like to know, shoot me an email and I will send them to you and you can study them on your own. But there's no requirement for this class that you actually understand where those come from. You just need to know what they are and be able to use them. Now, let's take a quick review of the binomial probability distribution from Lecture 11. We had 4 requirements for a binomial probability distribution. The first was the procedure must have a fixed number of trials. That was our N. Each trial must be independent. Okay, each trial must also have outcomes that are classified into 2 categories, typically referred to as a success or a failure. Now, a success, just calling something as a success doesn't mean that you might actually think of it as a success. A success may be that you lose a game. That just the way the problem is defined. The success is losing the game. Doesn't make sense logically, but in terms of the problem, it doesn't matter what you qualify as a success or failure. You can qualify death as a success. So it just depends on how you define the problem. And then the fourth requirement is that our probability of success remains the same in all trials. And if you remember, the probability of success is given by P, and the probability of failure is given by Q. We just talked about that. So we can solve this using the binomial probability formula or Excel. Now, as a further review, does anybody remember what the binomial probability formula is? Well, the probability that the number of successes equals X is equal to, remember we have, the first term is a combination. We have a total of n trials, little n trials, and we're going to pick X of them to be successes. So back from one of our earlier lectures where we dealt with permutations and combinations, we recall that equation for combination, if we have, in this case, it's going to be n choose X, that is equal to n factorial divided by n minus X. Don't know why I have that line that jumps all the way over there. N minus X factorial times X factorial. So that's n choose X. So we actually have that as part of the first part of our binomial probability distribution. So we have n factorial divided by n minus X factorial times X factorial. And then the next part we have is that we have to have a total of X successes out of our n trials. So remember, the probability of a success was P. So if we're going to have P successes, sorry, X successes. The probabilities multiply by each other because they're independent trials, so we have P to the X, and then we have a total of N minus X failures. That's how many are left over, so we have Q to the N minus X. So that is the binomial probability formula as a quick review. Now, when we approximate the binomial distribution using a normal distribution, we're going to set the mean, as I said, equal to mu equals n times p. Standard deviation is going to be sigma equals the square root of n times p times q. Don't forget the square root part. And we're going to assume then that this random variable has a normal distribution. We're going to be able to use our normal distribution, our standard normal curve, to solve this problem. So what are the steps in using a normal distribution to approximate a binomial distribution? First, you have to verify that your requirements are met, that n times p is greater than or equal to 5 and n times q is equal to 5. If it's not, then you're going to have to use that nice binomial probability formula that I just showed you, or you can actually use Excel. All right. The next step is you find the values of the parameters mu and sigma. We just talked about it. Mu equals n times p, and sigma equals the square root of n times p times q. Step 3 is to identify the discrete whole number x that is relevant to the binomial probability problem. And what do we mean by whole number x? That's the successes we're looking at, the number of successes. Whole number x. X equals the number of successes that we're interested in. Okay. Now that's step 3. Step 4, draw a normal distribution centered around mu, just like we always did. Then draw a vertical strip centered over x. Now this vertical strip is allowing us to estimate a discrete probability distribution using a continuous probability distribution. All right, if we were to integrate over a straight line or a single value, we would get 0. The area under the curve for a single value would be 0. So it would be meaningless to us. So what do? We add a little bit to each side of it. In this case, we're going to mark the left side of the strip with the number equal to whatever that x value is minus 1/2. And we're going to mark the right side with the number equal to x plus 1/2. So it gives us a little bit of area on both sides of that x line that we're interested in. Now we're going to consider the area of the entire strip to represent the probability of that discrete whole number itself. Again, that's because this is a binomial distribution, which is discrete, and the normal distribution is continuous. So we have to do a little bit of finagling, do a little bit to make it actually work. All right, step 5 here is to determine whether the probability you want is at the probability at least x, at most x, more than x, fewer than x, or exactly x. So that makes a difference whether you pick which side of the graph you pick, and we'll look at each of those individually in just a minute. All right, I want you to determine whether the value of x itself is included in the probability. So that is, if you do include x, then you have at least x or at most x. All right, if you don't, then you have either more than x, fewer than x, or I guess you could have at least x as well if you're including the value of x, and that's it. All right, shade the appropriate area either to the right or left of the strip, and then the interior of the strip if and only if x itself is to be included. The shaded region corresponds to the probability being sought. Okay, well, the next step is to, using whatever that x minus 0.5 or x plus 5 is in place of x, find the area of the shaded region. Compute the z-score. Use this value to find whatever area you're interested in to the left of your adjusted value of x. And then from there you determine what value you actually want. Wow, that's really confusing, isn't it? There's a lot of information thrown at you that it's just kind of difficult. Okay, got it. Let's look at an example. So, in a total of 431 NFL games that went into overtime, the team that won the overtime coin toss went on to win 235 of those games. Sudden death. First team to score wins. Okay. If the coin toss method is fair, teams winning the toss would be expected to win about 50% of the games. So we would expect half of the games, or 215.5 wins, in 431 overtime games. So assume there's a probability of 0.5 of winning a game after winning the coin toss. We're going to call that a success. So P equals 0.5. Find the probability of getting at least 235 winning games. That's this value we have up here. So that's where that came from. Okay. All right. So problem involves a binomial distribution. We have a total of n equals 431 trials and an assumed probability of success of P equals 0.5, which is what I just said. So if we can, let's use the normal approximation of the binomial distribution. So first we have to do our conditions check. And what were they? Well, we have to have NP greater than or equal to 5 and NQ greater than or equal to 5. All right, so NP will be 431 times P, which is 0.5, which gives us 215.5, not 2.15, 215.5, which is in fact greater than or equal to 5. And Q actually is going to be the same thing. It's going to be 431 times 0.5, which is also going to be 215.5. That's because the probability of our success and failures are the same, because we assumed a probability of 1/2 for success. So these are both greater than or equal to 0.5. I'll clean that up for you here a little bit, and if you haven't actually had a chance to copy it down, I'll give you a quick second to copy it down. Okay, so step 2 is to find the mean and standard deviation of the normal distribution. Well, we actually just found the mean when we did our check, because the mean is equal to mu equals n times p, which we found was 431 times 0.5, which was 215.5, right? So the next step is to find our sigma, which is equal to the square root of n times p times q, which is equal to the square root of 0.5 times 0.5 times 431, which I'm pretty sure is equal to 10.38. You can check my math if you don't believe me. Alright, so we want to find the probability of at least 235 wins. Oh, sorry. So what does that mean? So our x is going to be 235. We're going to do a vertical strip on the left and the right. So we're going to take 235 minus 0.5 for the left, and 235 plus 0.5 for the value on the right. So we're going to get 234.5 for the value on the left, and 235.5 for the value on the right. All right. Now, again, we want, what did we want? We want the probability of at least 235 wins. So that's including 235. So that means we're going to shade the area to the right of 234.5. So we want all this area down here in green. Okay. This area here in the middle is the area of exactly 235 wins. Just this right here. Okay. Now, next step is to find the z-score and use Excel or standard normal table to determine the probability. Alright, so our z-score is given by z equals x minus mu divided by sigma, which was 235 minus 215.5 divided by 10.38, and that value is 1.83. Now, we can jump over to Excel and find out what the probability is for 1.83. There we go. So, how do we do this? Well, we have equals binomial distribution. No, I have a z-score, so I'm going to do binom.inv, right? I want to find the probability from a z-score. Oh, no. we're using the normal distribution. So I'm not even doing the right thing. We want to do norm dot s dot inv. Okay, I'll get it right now. Norm dot s dot dist. The value we have is 1.83, and cumulative is going to be true. Okay, that gives us 0.966375. But remember, when we do one of these like this, it's actually giving us this area over here. All right, so we want to go back and do 1 minus that to get the actual value. Equals 1 minus that, which is 0.336. So down here, we're at 0.0336. Sorry, that's what I had. I just didn't say it correctly. So this probability is low enough to suggest that the team winning the coin flip has an unfair advantage. All right. Now, when we use the normal distribution like we just did, it's a continuous probability distribution. When we use it as an approximation for the binomial distribution, which is a discrete distribution, we use a continuity correction to the discrete whole number x by representing the discrete whole number by an interval given by x minus 0.5 to x plus 0.5. So we add and subtract a half. Okay, this is kind of what it does for us. All right, if we were going back to our example, we had 235 wins out of 431. If we wanted to look at least 235 wins, this includes 235 and above. So we do the area to the right of 234.5. That's that one. If we do more than 235, this does not include 235, so we do the area to the right of 235.5. That'll be a slightly different answer. If we do at most 235, it includes 235 and below, so we're going to do the area to the left of 235.5. Fewer than 235, which doesn't include 235, then we do 234.5 and below. And then if we want exactly 235, we do that interval between 234.5 and 235.5. Okay, now why do we even care about this? Why do we do this? The reason is because, remember, the binomial distribution is a discrete distribution. So if I wanted to find, like we were looking at, the probability that x is greater than or equal to 235, I have to find the probability that x equals 235 plus the probability that x equals 236 plus all the way up to the probability that x equals 431. So I would have to do a lot of these individually. All right, that is way too time consuming. Okay, so we do this instead, use the a continuous distribution, in this case the normal distribution, to estimate the binomial distribution, so we don't have to compute all of these individual binomial distribution probabilities. All right, here's an example I want you to try. In a recent poll of 1,004 adults, 291 chose professional athlete as their dream job. Assume that 25% of adults consider being a professional athlete their dream job. The result of 291 is more than 25% of 10,004. If you want to actually do the math, 25% of 10,004 would be 251. Okay, so it's higher, but not a lot higher. All right, well, what is the probability that among 1,004 random adults, 291 or more consider being a professional athlete their dream job? Okay, part B, if the value of 25% is correct, is the result of 291 unusually high? Meaning, was this an unusual sample, unusual group that they pulled? And then part C, does the result suggest that the actual rate is greater than 25%? So, go ahead and pause the lecture. You'll notice that there are two slides here that have the same thing. There's two different ways to do this. I'm going to show you two different answers. Two different ways to get the same answer. One using Excel and one using the method we learned today. So go ahead and pause the lecture and work it out on your own. Okay, if you haven't paused it and are not finished, I'm getting ready to show the answer, so you might want to pause it. Alright, so we could solve this as either a binomial or a normal approximation to the binomial. The nice thing is, like I said, we can use Excel using this true function, which gives you the probability mass function, which lets you actually do all those individual ones, add them all up. So what this is saying here, this is giving me the probability of going up to 290. Sorry, so 290 or fewer. Well, since we want to do greater than or equal to 291, that's the same thing as 1 minus this binomial distribution of at 290 successes out of 1,004 trials, the probability of success of 0.25, and then true means we include all of them or add them all up. So that gives us 0.0023. So it's a very small probability. All right. The next way we could do it is we could use the normal distribution with x equals 291, n equals 1004, p equals 0.25, and q equals 0.75. First we have to do our conditions check. N times p is 1004 times 0.25, which gives us 251, which is actually what I said. N times q is 1004 times 0.75, which is 753. And if you look this time, these values are not the same, they're actually different, which is more typical than the football toss, sorry, the football coin toss example we did. Alright, so since those are satisfied, that's supposed to be a check. Doesn't look anything like a check. Check, check. Then we can do mu equals n times p to get our mean, which is 251. Sigma equals square root of npq, which gives us 13.72. Alright, so we want to know the probability that x is greater than 291. So x equals 291, x minus 0.05 is 290.5, and x plus 0.05 is 291.5. But we want greater than or equal to, so we're going to use this lower limit here. Alright, and that's what we use down here. So we compute our z-score, 290.5 minus 251 divided by 13.72 gives us 2.88. And the probability associated with that, if you do your z-score back into Excel like we did, or do it in a lookup table, you're going to get 0.998. That's the area to the left. So we do 1 minus that and we get 0.0020. Now remember, before we got 0.0023. This is actually more precise because this is the binomial distribution. This is a normal approximation to a binomial distribution. But just realize we're down in the tenths, hundredths, thousandths, 10,000ths of a point. So we're 10,000th off. At that point, we're pretty good. Okay. All right. So if the value of 25% is correct, is this result of 291 unusually high? Well, because the probability of getting that is so small, 0.002 or 0.0023, then yeah, that result of 291 is unusually high. So this results do suggest that our actual rate is greater than 25%. Okay, so that's it for this lecture. Like I said, it was a fairly short lecture. Hopefully you understand everything. If you do not, please review the lecture and shoot me an email if you have any questions. Next time, we're going to consider different ways to estimate population characteristics and sample sizes. So it's going to be a change in direction of what we've been doing thus far. So we'll get ready for it because we're going to learn some new stuff. Thank you very much and have a great day.